Today we will discuss the confidence intervals. They are interval estimates for true population mean mu. Well, mu is something that we don't know. Always it's unknown. If mu is unknown, what we do is we take sample and calculate sample mean, which is given by x bar. But sample mean is just a point estimate. It is an estimate, but it is a point estimate. What do we mean by a point estimate? It is just a single value. It doesn't associate any probability of being correct as an estimate of mu. That's problematic. The reason is, let's say somebody else took another sample, calculated sample mean, and that's also a possible candidate as an estimate of mu. And his sample mean will be different from my sample mean. That most likely will be the case. In that scenario, whose sample mean could be more reliable? Well, if of course the other person had a larger sample size, according to the law of large numbers, his estimate should be more reliable than my estimate. But on the other hand, if both of us selected the same sample size, then whose estimate could be correct? Well, they both are correct as estimates. The reason for finding estimates is because we don't know the value of mu. Now, which one should be taken as an estimate? Now, that's a weakness the point estimates have. To avoid that weakness, rather than a point estimate, we prefer interval estimates. That means, instead of just one value, we say, all right, between this lower limit and that upper limit, the true population mean mu could exist. And we can also give a probability for that. Of course, it's based on the length of the confidence interval. Well, if you allow infinite length, that's from negative infinity up to positive infinity, in that case I can say, well, there's a 100% probability for the true mean to exist between those two values. Of course, yes. Any mean will exist between negative infinity and positive infinity. That's super trivial and silly. I don't want an interval like that. I need a nice small interval. Of course, if we can compromise that 100% a little bit. Let's say I allow a 5% error. So I go from 100% accuracy to 95% accuracy, which is still really reasonable. Within that 95% interval, I can reduce that negative infinity to positive infinity drastically to a very nice manageable interval, such as, for example, 20 to 30. Initially, 100% probability is from negative infinity to positive infinity. Now, just by compromising 5%, I reduced my interval from 20 to 30. Right? Now, if I can get such a small confidence interval, of course it is super small compared to negative infinity to positive infinity, just by compromising 5%, I will surely go for that option. Now, that process is called finding confidence intervals. Rather than just intervals, we put one additional word, confidence. The reason why we call it confidence interval instead of just interval is because we can specify a certain probability that your true mean will exist within this interval with that given probability. Therefore, we use the term confidence. There are two basic types of confidence intervals for true mean mu, which is unknown always. One confidence interval is called the Z confidence interval. The other confidence interval is called the T confidence interval. I will show you the difference between those two and how to derive those equations to find the confidence intervals. But remember one thing at this very starting point. This is a point where many students struggle. So let's be 100% clear at the starting point itself. Like I said earlier, there are two types of confidence intervals. This is the very first thing you have to remember regarding confidence intervals. One type is Z confidence intervals. The other type is T confidence intervals. The most important point you have to remember is when to construct Z confidence intervals and when to construct T confidence intervals. Now, I'm going to tell it to you right now, and you have to remember it for the rest of the semester. We do Z confidence intervals if the true standard deviation, which is sigma, is given to you. I would say if sigma is given, or I would say if sigma is known, all right? In that case, you go for Z confidence interval. We do T confidence interval if sigma is unknown, okay? So if sigma is not given. I have seen so many students making mistakes of these calculations. Please remember, we do Z confidence interval if sigma is given. We do T confidence interval if sigma is not given. What are those intervals? All these details can be addressed later. First, remember there are two types, and remember when to use each type. As always, I have posted this lecture on Canvas. Please go ahead and download that, and then you can watch the video and complete the points with me. The 100% probability confidence interval is the trivial confidence interval, which is totally worthless, but I will just write it down as a starting point. 100% confidence interval. This is my abbreviation for the confidence interval, C.I. confidence interval, okay? 100% confidence interval is from negative infinity to positive infinity. That's trivial, no use whatsoever. But what we are going to do is, we are going to compromise a small amount of accuracy, such as 1%. If I compromise 1%, that 100% confidence interval reduces to 99%. If I compromise 5% of accuracy, the confidence level will reduce from 100% to 95%. If I compromise 10%, that 100% confidence interval will now be reduced into 90%. Of course, nobody compromises more than 10%. For all practical purposes, the maximum level of error that you will have to allow will be naturally 10%. For most of the statistical analysis, the default magic level of error is just 5%. So we almost always go for 95% confidence intervals. Okay? So these are the other popular intervals. So this is trivial, no use, and now here are the popular confidence intervals. We have 99% confidence intervals, you have 95% confidence intervals, and you have 90% confidence intervals. Well, of course, anybody can create any other confidence level as well. For any level of confidence, I will show you how to generate the equations, but I just want to tell you as a starting point that these are the most popular confidence levels. So when you construct a 99% confidence interval, what's the error that's allowed? The error that's allowed is 1%. For 95% confidence interval, the error that's allowed is 5%. For 90% confidence interval, the error that's allowed is 10%. Well, I don't want to generate an equation for every single confidence level, so I will write down in general the level of error that's allowed is alpha percent, okay? So I will let alpha percent be the error allowed. Now this is the very first type of error that you're going to see in an intro statistics class. So actually this is therefore called type 1 error. The reason why it is exactly called type 1 error can be seen when we start inferential statistics at this point of time. That's the first error you saw in this class, and which will be allowed. So we'll call it just type 1 error without looking at the reasons why it is called type 1. Okay? At this point of time, we are not going to see the reasons of calling it type 1, but I will explain you why it is called type 1 later. Okay? So let alpha be the type 1 error allowed. Then the confidence intervals can be written in general as (100) minus alpha % confidence intervals, correct? So remember that for 99% confidence interval, your alpha will be 1%. In decimals, your alpha is 0.01 for 99% confidence interval. For 95% confidence interval, your alpha is 5%. Using decimals, your alpha will be 0.05. For 90% confidence interval, your alpha is 10%. Using decimals, it's alpha equals 0.10. These number of decimals will be very important, number of zeros and so on. So please pay attention when you write them down using decimals, okay? Now we can slowly construct 100 minus alpha % confidence intervals. Let's see how to do that. In order to derive the equation for the confidence intervals, I'm going to use the central limit theorem. So what's the central limit theorem? We said we can have a random variable x, which technically follows any distribution. So I will write x is distributed any distribution, dist, just to stand it for any distribution, okay? With a mean of mu and a variance of sigma squared. Now that looks somewhat like the normal distribution, but don't be confused. X doesn't necessarily have to follow a normal distribution. So x can technically follow any distribution, and for any distribution, we can find its mean and variance. Okay? For example, if x follows uniform distribution from A to B, the mean will be equal to A plus B divided by 2. That will be taken as the value of mu. The variance will be equal to B minus A, everything squared, divided by 12. That will be taken as sigma squared. On the other hand, x can also be a discrete random variable. Okay? For example, if x follows Poisson lambda distribution, then both mean and variance will be equal to lambda, which means mu will be equal to lambda, sigma squared will also be equal to lambda. So we are completely comfortable with those. Okay? No matter what distribution that x follows, we know how to find the mean, we know how to find the variance, and I'm going to label them as mu and sigma squared respectively. Okay? And the central limit theorem says you take samples of size n, calculate sample mean, which is x bar, then x bar follows what distribution? No matter what your original distribution is, x bar should follow a normal distribution. Normal distribution with the same mean as the original random variable, which is mu, and the variance will be now different. Instead of sigma squared, the new variance will be sigma squared over n, where n is the sample size. So that's all about the central limit theorem. We discussed the central limit theorem in our previous lecture. We discussed completely and we saw examples as well. Okay? So we are going to discuss the first application of the central limit theorem today, which is the confidence intervals. Okay? As the very first part, we are going to construct 100 minus alpha % z confidence intervals. You still don't have to write down anything specific under point number 1. Okay? I'm going to derive the equation, and then finally we can write down that equation. All right, so I'm going to use the central limit theorem, and let's draw the distribution of x bar. So it's a normal distribution, which means it's a nice symmetric bell curve. So let's assume that this is your distribution of x bar. Okay? What should be the midpoint? the midpoint, which is the median, should also be equal to mean, because this is a symmetric distribution. For any symmetric distribution, we said mean should be equal to median. Well, of course, you already know that the normal distribution is symmetric around its mean, which is mu. So this point is mu. Now, tell me, what should be the total area of this distribution? The total area is 1 unit. Or in other words, the total area is 100%. Okay? So if the total area is 100%, and also I know that the left endpoint is negative infinity, the right endpoint is positive infinity. That 100% is actually from that negative infinity to positive infinity. That actually is the 100% confidence interval. That means if I need a 95% confidence interval, all I have to do is to take 95% of the area and find two limits, one from the left and the other one from the right. So if I bracket whatever the probability I need, I would say L and U, where L stands for the lower limit, U stands for the upper limit. I can do it as a symmetric interval so that I have the same distance from the center to the right and to the left. That means if, for example, I need 95% confidence interval. So the area between L and U will be 95%. And area to the right from U and area to the left from L will be 5%. If I need a 99% confidence interval, I need to select L and U so that between L and U I have 99%. To the right from U plus to the left from L I have 1%. Now if I wanted 90% confidence interval, I can do the same way. Between L and U I will need 90%. To the right from U and to the left from L, a total of 10% is what I need. Now, in general, we are going to construct 100 minus alpha percent confidence intervals. That means 100 minus alpha should be the area between the lower limit and the upper limit. That means the summation of the two shaded areas should be equal to alpha percent. Now this is a nice symmetric curve. When I select L and U to be symmetric with respect to mu, these two areas should be equal to one another. That means the total is alpha, which means each area should be half of alpha. Now, I can find U and L, isn't it? So if I find those two, then that's that interval I need. And we can call it the confidence interval. Now, how do we find it? Well, using our calculator, we can go to distributions, select number 3, inverse normal, and we can find, let's say, L. I need to find L first. Then I can enter area to the left as this is half of alpha. Okay, if it is a 90% confidence interval, alpha will be 10%, half of alpha will be 5%, which means 0.05. That can be entered. And then I will have to enter mu and sigma. Now, do I know the value of mu? I'm in trouble. I don't know the value of mu. Then what? Without knowing the value of mu, that calculation cannot be done. That's the obstacle I have. But luckily, there's a mathematical way to get rid of that obstacle. Now, tell me what we mean by the standard normal distribution. The standard normal distribution is a normal distribution whose mean equals 0 and whose variance is equal to 1. And what we mean by the z-score. The z-score is a mapping from any normal distribution into the standard normal distribution. For the standard normal distribution, I know both mean and variance. Mean is equal to 0, variance is equal to 1. Technically, I know everything regarding the standard normal distribution. So, what I'm going to do is, I'm going to map this distribution, which is a normal distribution, into the standard normal distribution through z-score. Okay? So, here's my z distribution for the standard normal distribution. We know that standard normal distribution is given by z with 0, 1, normal 0, 1. And I'm going to draw that distribution. Let's say this is my standard normal distribution. What I'm going to do is, I'm going to map this point u into a corresponding point on the z distribution. So, if I calculate the z-score of this u, I will find some z value, let's say z sub u. Now, what's the connection between u and z sub u? They will have the same areas to the right. That means u to the right, that area should be the same area as zu to the right. We've seen one calculation like that in the discussion of the normal distribution. If you cannot remember, you can go back and check that. So this area will be half of alpha. And I know this one. How do you calculate zu from u? Remember the z-score equation? Z-score is given by the value of your random variable, let's say x, that minus the mean of the distribution of x divided by the standard deviation of the distribution of x. Now I'm talking about the distribution of x bar. So the mean is equal to mu and the standard deviation is equal to the square root of this, because this is the variance. Okay? So for distribution of x bar, remember that for the distribution of x bar, mean equals mu and variance equals sigma squared over n, which means the standard deviation should be sigma over square root n, because I need to take the square root of the variance in order to find the standard deviation. So if I take the square root of sigma squared over n, it becomes sigma over square root n. Okay? All right, I've got all that. And then I can find z sub u, z-score. So the z sub u will be equal to the value of x, which is u, minus the mean. The mean is mu, divided by the standard deviation, which is this guy, sigma over square root n. Right? Now from that, I'm going to find the upper limit u. So I can multiply both sides of this equation by sigma over square root n. Then I have sigma over square root n times zu equals u minus mu. That means my u, the upper limit, should be equal to sigma over square root n times z sub u plus mu. I will just leave it there as it is. Okay? Now, what I'm going to do is, I will map the lower limit also onto the z distribution. So, if I map that lower limit into the z distribution, I will find a corresponding Z score, let's label it as Z sub L. So the connection between L and Z sub L is also just like earlier. Area to the right will be equal. Okay? Area to the right will be equal also means that areas to the left will be equal to each other. So this area will be same as that shaded area. So this is half of alpha. So this should also be half of alpha. Now we can write down an equation for Z sub L. Z sub L will be equal to the lower limit minus mean divided by the standard deviation, which is that sigma over square root n. And just like earlier, I can simplify this one. I can multiply both sides by sigma over square root n. And then sigma over square root n times Z sub L will be equal to L minus mu. Then I can add mu to both sides. And by doing that, I get the lower limit L equals sigma over square root n times Z sub L plus mu. Now, tell me the connection between Z sub L and Z sub U. They are negatives of one another, right? Because this is from the Z distribution and it is symmetric around 0. So the midpoint is 0. And I have half of alpha from negative infinity up to this point. I have half of alpha from positive infinity up to that point. That means these two must be of equal distances from 0. That means one should be positive, the other one should be negative. Okay? And the sizes must be equal to each other. So that size, since this is half of alpha, I will just label it as just Z half alpha. So Z sub U can be seen as equal to Z half alpha. I will assume this is a positive value. And the same way, this Z sub L can be seen as Z half alpha value, but it's going to be a negative value. Okay? So I will write this as negative Z half alpha. Now that value can be easily found using our calculator. Okay? We can go to inverse normal and the area is just half of alpha. So which is selected from the confidence level. If it is a 95% confidence level, alpha will be 5%. Half of alpha will be 0.025 therefore. Okay? So half of alpha is known and mu is 0 and sigma is 1. That means I definitely know these points. Alright, so that actually helps. So I'm going to replace this ZL and ZU with these values. Okay? So ZU will be replaced with Z half alpha. So this will be written as Z half alpha. Now that's for the upper limit. Okay? And for the lower limit, I will write negative Z half alpha for Z sub L. Instead of Z sub L, I'm going to write a negative Z half alpha. So it will be now Z half alpha and it will be negative. So I show negative symbol. Okay? Now I have fairly constructed what I need. But still, that problem of mu is there. I completely know this part, I completely know that part, provided sigma is known to me. That means I'm slowly moving into that Z confidence interval. We said Z confidence intervals are constructed when sigma is known. Okay? So sigma should be used. We assume that sigma is available to us. I have already used Z values. Now these Z values are called Z critical values. That's why we call those intervals the Z confidence intervals. Now what I need will still be mu. Mu is there. Then what? I'm going to replace mu with the sample estimate x bar. I'm going to replace mu with the sample estimate x bar, because we know x bar is an estimate for mu. So I'm going to use that. So mu will be written as x bar. Mu will be written as x bar. I'm done. The calculation completed. This is the lower limit, this is the upper limit. So we can write down an equation. I will write somewhere here. 100 minus alpha percent, I would say z confidence interval, is given by this equation. I have a lower limit, comma, upper limit. It has to be written as an interval using interval notation, which means you have to write it inside parentheses. First, you write the starting value, the smaller value, comma, the larger value or the ending value. Okay? So I will write down this slightly differently, just to look nicer. X bar will be written first because it may be written as a positive value, and the rest is negative for the lower limit. So this is our lower limit. So I'm going to start with x bar minus sigma over square root n times z half alpha. That's your lower limit. The upper limit is, I will write x bar first once again, x bar plus sigma over square root n times z half alpha. All right, so if you look at most of the text, often they flip these two terms as well. They first write z half alpha and then write sigma over square root n. Either way is fine, okay? You just have to multiply sigma and z half alpha and all that divided by square root n. That's if you are going to use the equation. Anyways, this is what I will write as point number 1. This is all you need. That's the equation. This is 100 minus alpha percent, two-sided z confidence interval for true mean mu. How would you interpret this confidence interval once the values are found? The confidence level is 100 minus alpha percent. So we have to be specific about that. We will say the true mean of our random variable, you have to use the given name of the random variable, will be between this specific lower limit and that specific upper limit with a probability of 100 minus alpha percent. That's the full interpretation of this confidence interval. All right, let's move on to point number 2. There's a data set given. There are 6 measurements of electrical conductivity of a certain type of iron rod at 293 Kelvin, given that sigma equals 0.1. The readings are given. Construct a 95% two-sided confidence interval for the true mean electrical conductivity. Interpret the constructed confidence interval. Well, for your class, you don't have to remember this equation, but I just wanted to show you that this is how the calculator calculates the confidence interval. Your calculator has a nice shortcut to obtain this answer. Let's go to the calculator TI-84. Here is the calculator. We also have the question on the screen, and let me go ahead and enter the dataset first. In order to enter the dataset, you have to press Stat, select Edit, number 1, Edit, and Enter. And we can enter the given dataset into the list L1. The first data point is 10.08, enter. The second data point is 9.89. The third data point is 10.05. The fourth data point is 10.16. The fifth data point is 10.21. And the sixth data point is 10.11. Hit enter. All the given data points were entered into the list L1. Now I have to construct a 95% two-sided confidence interval.
sigma is given as 0.1. Because sigma is given, we construct a z confidence interval. In order to construct the z confidence interval, you have to once again press stat, use the right arrow key and select tests. And then you have to select number 7 z interval. Select number 7 z interval, hit enter. Now you have to define the input method. We had the dataset. We didn't have the statistics. What are the statistics? For example, if you had the sample mean and the number of data points you have, they are called statistics. In that case, the input method can be selected as statistics and then you can hit enter. In such situations, that means when you don't have the data set, instead the calculated statistics are given, you can enter those values into the calculator at that point. You can enter sigma, you can enter x bar, and also you can enter n, where x bar is the sample mean and n is the number of data points. Now for this question, I don't have statistics. Instead, I have the dataset and we have already entered the dataset into the list L1. Therefore, I will select input method as data and hit enter. In the next line, I must enter the given sigma value. Sigma is equal to 0.1. Then you have to define the list where you entered your data points. We entered all the data points into the list L1. If that wasn't there, you can define it right here as second and 1. That's how you define list label. If you entered your data into list L2, you will have to press second and number 2, so that list will be taken as L2. Always frequency is equal to 1. Confidence level. I need a 95% two-sided confidence interval. Therefore, the confidence level is 0.95. That's all you have to enter for the z confidence interval using the data. Select, calculate, and then hit enter. You hit enter only one time. The confidence interval is shown on the first line. The lower limit is 10.003. The upper limit is 10.163. Therefore, the 95% z confidence interval for the true mean electrical conductivity is from 10.003 to 10.163.
So here's the confidence interval that we calculated. I got 10.003 as the lower limit and 10.163 as the upper limit. So this is a 95% confidence interval, and we constructed it for the mean electrical conductivity, true mean electrical conductivity. So the interpretation should include those pieces, okay? I would say there is a 95% probability for the true mean electrical conductivity to be within 10.003 and 10.163. I think the units are not given, so we can just leave the answer as that. So these pieces are very important. You have to specify the probability level, in this case 95%, and of course for most of the future calculations also, it will be 95%. And you have to use the word true mean, that will always be there, and you have to use the name of the random variable. And you should also specify the lower limit and the upper limit. And also you have to include the units if they are given. If I ask you to do a calculation of a confidence interval, and if the question carries 5 points, only 2 points will be assigned for this calculation. Because you don't have to do that many things. You just have to enter the given numbers and press the button in your calculator and you get this answer. Interpretation is worth more points than that. So this is 2 points, and here you will get 3 points for the interpretation, okay? Please keep that in mind. All right, let's move on to the point number 3, 100 minus alpha percent two-sided T confidence intervals. We construct T confidence intervals when sigma is unknown. The confidence interval that we previously calculated is called a 100 minus alpha percent Z confidence interval. Let's write down that equation one more time. We have a lower limit of x bar minus, we write z half alpha times sigma over square root n. You may flip these two if you like, that's how we wrote earlier. And the upper limit is x bar plus z half alpha times sigma over square root n. Now this confidence interval is constructed for mu. That's because mu is unknown. When we don't know mu, the calculation of sigma also doesn't make that much of practical sense. But on the other hand, if you have plenty of past data, even though we don't know the true mean, we might still know the true variance. That's a bit advanced concept. But using that variance, we can, of course, practically go for a confidence interval like this, for the true mean. But most of the real-life applications, especially if you don't have large piles of past data, we don't know both mu and sigma. Or in other words, we don't know the true values of the mean as well as the variance. Then what? In that case, how can we construct a confidence interval? For that purpose, we have 100 minus alpha percent T confidence intervals. So here's the equation. Well, we start with x bar, and this guy, sigma, is unknown. Well, of course, in the previous calculation, we had mu, and we said we don't know mu, therefore we are going to use x bar. Now I have another term which is unknown, which is sigma. So I'm going to replace that sigma with its corresponding sample estimate, which is the sample standard deviation given by S. So I'm going to write that part with S. And the bottom is, of course, square root n. How about this value, z? That z-score calculation requires sigma. And we get z half alpha accordingly. Now, for that previous calculation of the z-score, what we didn't know was only the mean. Now I don't know two pieces, mean and variance. That means I'm more uncertain about my findings. I'm more uncertain about my findings means to reach the same level of accuracy, which I reached using the standard normal distribution, I will need to go further away from the midpoint, unfortunately. Now, is there a distribution that will give me more distant points with respect to the midpoint compared to the standard normal distribution? It should still resemble the overall shape of the normal distribution to hold those characteristics. So tell me a distribution that looks like the normal distribution, still has more tail areas. We have the T distribution, remember? The T distribution has thicker tails. Thicker tails means this is your T distribution. So the blue line, let's say it's our standard normal distribution. Now in standard normal distribution, when I keep half of alpha, if half of alpha comes up to this point and up to that point, this is my lower, this is my upper, and we know this is half of alpha. This is also half of alpha. Now, if I keep half of alpha in this red curve, will it come up to this point? No, half of alpha can be covered before reaching this point of U. Okay? So half of alpha may be up to here. This shaded area could be half of alpha. Same here, somewhere here. This shaded area could be the total half of alpha. You can now see that the lower limit has shifted more towards negative infinity and upper limit has shifted more towards positive infinity. Or in other words, the lower limit has moved further away from the midpoint and the upper limit also has moved further away from the midpoint. Okay, that exactly is what we need. So what we are going to do is we go for the t distribution instead of the z distribution when it comes to unknown sigma. So I will write down this guy as t half of alpha. But on the other hand, the t distribution also depends on degrees of freedom. Remember, as degrees of freedom increases, the t distribution gradually converges onto the standard normal distribution. Of course, it makes sense, because as sample sizes increase, the reliability of our estimates will also be improved. To address that, we have degrees of freedom always associated with the t distribution. So instead of writing t critical value, these are called critical values, as just t half alpha, we will also indicate its corresponding degrees of freedom. So this equation is written as t half alpha, comma, df. That's your lower limit. The upper limit will be similarly written, x bar plus t half alpha, df, s over the square root n. That's the upper limit. Once again, you don't have to remember this equation. Luckily, your calculator has that function as well. Let's move on to point number 4. For the question in number 2, assume that the true standard deviation sigma is unknown. Construct a 95% two-sided confidence interval for the true mean electrical conductivity and interpret the constructed confidence interval. All right, let's do that.
Here's the calculator. We are going to construct a t confidence interval this time. We have already entered our data set, so I'm not going to show you the step of entering the data again. Instead, I will straight away go ahead and construct the t confidence interval. First, I have to press stat, and then I can select tests, and then you have to select number 8 t interval. Select number 8 t interval and hit enter. We have entered our data into the list L1. Therefore, input method should be data. Select data and hit enter. Then you have to define the list where you entered the data. We entered our data into the list L1. Frequency is always equal to 1. Confidence level. I need a 95% two-sided t confidence interval. Therefore, the confidence level should be 0.95. Select calculate and hit enter. The first line shows you the 95% t confidence interval. The lower limit is 9.9673. The upper limit is 10.199.
I got 9.9673 as the lower limit and 10.199 as the upper limit. This is that confidence interval. This is again constructed for the true mean electrical conductivity. Showing these two values will only give you just 2 points out of 5 total assigned for a question like that. And the other 3 points will come for the interpretation of that confidence interval. So I will say there's a 95% probability for the true mean electrical conductivity to be within 9.9673 and 10.199. Okay, that's the complete interpretation of the confidence interval. Now there's another additional question under point number 5. In that question, the data set is not given to you, but the statistics are given. The mean compressive strength of 8 samples of cement is found to be x bar equals 6,012 kilograms per square centimeter. That means n equals 8 and x bar is the given value. Okay. So for this question, when you construct the confidence intervals, you will have to change the input method into statistics because we don't have the data set. Okay. Part A, assume that the true standard deviation is sigma equals 100. Construct a 95% two-sided confidence interval for the true mean compressive strength and interpret your answer. I will leave it for you to do. Sigma is given. That means what's the type of confidence interval I should select? Is it Z confidence interval or T confidence interval? It's a Z confidence interval because sigma is given to us. Part B, assume that the sample standard deviation S equals 100. Construct a 95% two-sided confidence interval for the true mean compressive strength. Interpret your answer. This time, I cannot use sigma. The given standard deviation is a sample standard deviation. That's why it says S equals 100. That means I must go for T confidence interval. And then part C, compare the two confidence intervals constructed in A and B. Explain why is the confidence interval in part B wider than the confidence interval in part A. Why? Because in part B, we constructed a T confidence interval. For both calculations, as standard deviation, in part A as sigma and in part B as S, we used 100. Okay. Here we used 100, here we used 100. Of course, n is 8 and sample mean is the given value. So everything stayed the same for both calculations except these values. These are called critical values. Z values are called critical values in that Z confidence interval calculation. These T values are called T critical values in that T confidence interval calculation. The reason for T confidence intervals to be wider is because the T critical values are larger compared with Z critical values, making the final answers more away from the midpoint. Let's see how to find those critical values for a couple of confidence intervals. So we'll do a simple example real quick, how to find those critical values. Of course, we have Z critical values and T critical values. Okay, so we'll do two simple exercises. First one is to find Z critical values, Z half alpha values. Okay. Of course, we have 99%, 90%, and 95% as the standard confidence levels. So we will find Z critical values for those confidence levels. Okay, let's say for 90%, and for 95%, and for 99%. Okay, 9% means your alpha is equal to 10%. Okay, and always Z half alpha stands for keeping half of alpha on each tail. And Z distribution follows normal 0, 1. When we know the values of alpha, we can easily find those critical values. Okay, we'll find the negative value or the positive value, and we can simply drop the negative symbol because this equation already contains the negative and positive values. And what we substitute in these spaces is only the numerical positive value. For 90%, we know alpha is equal to 10%, which means alpha equals 0.1. We are going to keep half of alpha on each tail, which means alpha divided by 2. So 0.1 divided by 2 is 0.05. Now we go to distributions in your calculator and select inverse normal, and area is 0.05.
I need to go to distributions, second variables, that's where I have distributions, and then I have to select inverse normal, which is given under number 3. Select number 3 inverse normal, hit enter. We said the area is 0.05. In this calculator, you can enter area as 0.05 simply and select whether the tail is left, center, or right. But most of the older versions of the calculator, you cannot see this fourth line to select the tail. In those older versions of the calculator, area means area to the left. So when you simply enter 0.05 in your calculator, if it is an older version, your answer will be a negative value. But for this calculator, I can select tail as right. The mu value is 0, sigma value is equal to 1. because we are working with the z distribution. For the z distribution, mu equals 0 and sigma equals 1. Now, if I select the tail in this calculator as left, my answer will be negative. If I select right as the tail and hit enter, now my answer will be positive. In all the versions of the calculator, you will not have that option. To obtain positive answer, you will have to enter 0.95 because area always means area to the left in all the versions of this calculator. I have entered everything necessary and I will now select paste and hit enter. And you have to hit enter again. The critical value is 1.645.
So we have to go to distributions, select number 3 inverse normal, and area is 0.05, half of alpha. Okay, 0.1 divided by 2 is 0.05. And your mu is, we are working with the standard normal distribution, so the mu is equal to 0. The sigma value is equal to 1. Okay. So enter them as that, and then you can select paste and hit enter again. You get the answer. And you can drop the negative symbol. So if you do the calculation correctly, z half alpha value will be equal to 1.645. Similarly, you can find z half alpha value for 95% confidence interval. For 95% confidence interval, that z half alpha value will be equal to 1.96. For 99% confidence interval, half of alpha will be equal to 0.005. And if you do the calculation, you will find that z critical value will be equal to z half alpha equals 2.576. So that's how the z critical values are found. All three of these critical values are very important actually. They are standard values and they don't depend on the degrees of freedom. So always you just have to look at the alpha level and then you can figure out these critical values. They are fixed and it's very helpful if you can remember these values, because in the future we are going to repeatedly use these values for various calculations in inferential statistics. But on the other hand, next we are going to see how to calculate the t critical values. The t critical values are not standard. For each case, we have to find the t critical value using a table or using technology. The reason is t distribution depends on the degrees of freedom. So whenever you have a sample of size 10, you have a specific degrees of freedom. So how do you find degrees of freedom? Degrees of freedom is equal to the sample size minus 1, n minus 1 always. Okay? So if you have a sample of size 10, degrees of freedom will be equal to 9. If you have a sample of size 15, degrees of freedom will be equal to 14, and so on. We'll do an example. T half alpha values. I will do it for one alpha level. Let's say 95% confidence interval with sample size of 10. Okay. Sample size is 10 means your degrees of freedom should be equal to 9. So the t distribution is also similar to the normal distribution. It's going to be a nice symmetric bell curve. So we are going to keep half of alpha on each tail. So alpha is 5% for this. So half of alpha will be 2.5%. In decimals, it is 0.025. And then you can go to distributions, select inverse t, and then you can enter the area. In that calculation, area is always area to the left. So we are going to enter, if you need that negative value, you can enter as 0.025. If you prefer the positive value, you will have to enter 0.975. Why is that? Because here's your t distribution, similar to the standard normal distribution. And so this is the degrees of freedom equals 9 case. Alpha is 5% for this example, so we're going to keep half of alpha on each tail. Half of alpha means 0.025. So this tail will also have 0.025. In your calculator, area means always area to the left in the inverse t function. So if this is 0.025, entire area to the left will be 1 minus 0.025, which is 0.975. Okay, that's the reason. Well, either way is fine. You can simply enter 0.025 and get the answer. Your answer will be a negative answer. You can simply drop the negative symbol and write down the critical value just as the positive answer. Okay, so let's go to your calculator.
Here's the calculator again. For the t critical value also, I have to go to distributions, second variables, that's where we have distributions, and then we have to select number 4, inverse t. Now some older versions of the calculator doesn't have this function. They will have to find an alternative newer version of the calculator, at least for the exams. Select number 4, inverse t, hit enter. Area, if I enter 0.025, I will get a negative answer, which is completely fine because I just have to drop the negative symbol. If you want the calculator to provide you the positive answer, area should be 0.975, because in the inverse t function, area always means the area to the left from the point we need to find. Degrees of freedom. We said it is 9 for that specific example because we had a sample of 10 data points. Degrees of freedom is calculated as n minus 1. 10 minus 1 is equal to 9. Select paste and hit enter again. The required answer is 2.262. You can safely drop negative symbol when you write down the critical value for the confidence intervals.
I got 2.262. So this is the critical value that corresponds to 95% confidence interval if you used a sample of size 10. Let's move on to the next point. And here's an example given under point number 6. A rocket motor is formed by binding an igniter propellant and a sustainer propellant together inside a metal housing. The shear strength of the bond between the two propellant types is an important characteristic. Part of a data set on shear strengths is given below. I think this is actually the complete data set. Construct and interpret a 95% two-sided confidence interval. Well, you of course know how to do that, so I will leave that question to you. Now, is it a t confidence interval or a z confidence interval? Well, we have to read carefully, and we don't see the value of sigma given anywhere in the question. That means we have to go for a t confidence interval. You know how to do it. Go for that. Let's move on to point number 7, the sample size calculations for sigma known cases. Well, it is just one application of the central limit theorem and the confidence intervals. So that's the reason why we discussed the sample size calculation at this point. Of course, we've already used a previously calculated sample size when selecting samples using the simple random sample and stratified random sample. In those sections, we didn't specifically mention how to determine the number of subjects that should be selected for our sample. What we did was we just said we're going to select a sample of size 15, for example. We explained how to select 15 individuals, maybe as a simple random sample or a stratified random sample. But the problem is we didn't mention how to determine that initial targeted sample size. Now, today, we are also going to see a way to figure out that initial sample size. We can do that using the confidence interval method, but this equation will tell you only the sample size when sigma is known. Okay? Now, we said 100 minus alpha percent z confidence interval is given by x bar minus z half alpha sigma over square root n, that's the lower limit, and the upper limit is x bar plus z half alpha sigma over square root n. Now, this quantity, if you pay attention, it's same. For the upper limit, you add that to x bar, and for the lower limit, you subtract that from x bar. So let's label it as error, okay? E, error. So this confidence interval can also be written as x bar minus e and upper limit as x bar plus e. Now what is this E? Well, E equals Z half alpha times sigma over square root n. Now let's say I would like to have my 95% confidence interval within a specific limit. I would like to have the difference between lower and upper limits as just 10 units. I need that accuracy. Of course, the difference of the upper and lower limits will be equal to 2e, right? Because x bar plus e minus x bar minus e. So x bar and x bar will be cancelled. With the second minus, this negative e become positive. Okay, so 2e is the width of this interval. When I determine that the width of the confidence interval, say for example, to be equal to 10, 2e equals 10, that means e equals 5. Once e is determined, we can find a corresponding sample size. I can just multiply both sides by square root n, divide both sides by e, then I get square root n equals z half alpha times sigma over e. That means your n should be equal to the square of all that. Now this gives you an estimate for the sample size. Of course, sigma should be known in order to use this equation. And z half alpha, we already found how to find that. Okay, for 95% confidence interval, which is the most popular confidence interval, z half alpha should be equal to 1.96. E is whatever you like and may be given in a question. So just plug in those values and simplify and you get the answer. And remember, as always, sample size calculations should be rounded up. Even if you ended up with, let's say, 16.1, n should be taken as 17, not 16. Okay? Always, sample size calculations should be rounded up. All right. And here's an example given under point number 8. Find the required sample size to predict the true mean temperature with a margin of error of 3 with 95% accuracy if sigma equals 5. That means your E equals 3, margin of error is equal to 3, sigma is given as 5, and what should be Z half alpha? It's a 95% confidence interval. So we found earlier, for a 95% confidence interval, Z half alpha should be equal to 1.96. So that's why I said, if you can remember those Z critical values, those will be very helpful for the rest of the semester. Then you can just plug in those values and simplify this equation and get the answer. Basically, that's all about chapter 16, but we will need some more. That's single-sided confidence intervals. So let's now see what we mean by a single-sided confidence interval. Let's move on to point number 8, single-sided. We start once again with Z confidence intervals, and then we will discuss single-sided T confidence intervals as well. There are some random variables for which I'm not interested in two limits. For example, let's say I would like to have the tensile strength of the raw materials, aluminium maybe. I need to make sure that it actually has at least a specified minimum tensile strength. The upper limit, I'm not interested. I need at least the tensile strength to be greater than a given value. Upper limit, I'm open. That means I have a fixed lower limit. The upper limit, I will just leave it as positive infinity, I don't mind that. And similarly, there are some cases, some random variables, where there is a specific upper limit. I don't mind the lower limit. Okay? So for example, the cost of something. I don't need to go beyond a certain upper limit. The lower limit, I of course don't mind. I mean, if it is negative infinity, that means the merchant is going to give me money for me going and buying it from him. No, that will not happen as that, but relatively smaller lower limit, I don't mind that. Okay, so I would say just negative infinity for theoretical purposes. The upper limit is what I need. Okay, I need an upper limit, and I will not go beyond that. So occasionally I will need to find these kinds of confidence intervals as well for certain random variables based on our interests. Let's see how to find that kind of confidence intervals. We can actually start with two-sided confidence intervals. We will first look at the two-sided Z confidence interval real quickly one more time. In a two-sided Z confidence interval, we had x bar minus Z half alpha sigma over square root n, that was the lower limit, and x bar plus Z half alpha sigma over square root n, that was the upper limit. What we did in that scenario is, here's our Z distribution, and we kept half of alpha on each tail. Now in single-sided confidence intervals, what we do is, we don't keep half of alpha on any tail. If I need an upper confidence interval, the upper confidence intervals are the confidence intervals with a fixed lower limit and upper limit is positive infinity. These are called upper confidence intervals. And if you have negative infinity and a fixed upper limit, those are called lower confidence intervals. So basically, I will need to keep complete alpha instead of just half of alpha on whichever the tail I need. Okay? Let's say I will keep complete alpha on this tail. Then I get a lower limit and upper limit will be positive infinity. Now, how can I write down an equation for this guy? It will be similar to this guy, okay? This equation. So, I would say 100 minus alpha percent upper Z confidence interval. There is a fixed lower limit. That fixed lower limit will have this same shape. It will be x bar minus, instead of Z half alpha, I will now have complete Z alpha, Z sub alpha, and sigma over square root n. Upper limit is positive infinity. So you write it as that. And similarly, if I need 100 minus alpha percent lower Z confidence interval, the lower limit will be negative infinity and upper limit will be similar. This term will be replaced with Z alpha instead of Z half alpha. Okay? So it will be from negative infinity up to x bar plus Z alpha times sigma over square root n. That's it. So if you like, you can remember the equations, but remembering the equations will not be required because we have our calculator. But unfortunately, there's a small obstacle. The calculator doesn't have single-sided confidence intervals. That's for a reason. Calculator is smart, actually. We practically don't need two different functions for two-sided confidence intervals and single-sided confidence intervals. We can do a small trick. Now here's the trick. Think about 100 minus 2 alpha percent confidence intervals. -2 alpha percent two-sided confidence intervals. It may be 99%, it may be 95%, it may be 90%, maybe 80%, maybe whatever the other percentage value that you need. Well, of course, if I need 99% single-sided confidence interval, upper or lower, alpha is equal to 1% in that case, which means 100 minus 2 alpha percent means 98%. If I need a 95% single-sided confidence interval, alpha is equal to 5%, 2 alpha is equal to 10%, 100 minus 2 alpha will be therefore equal to 90%. If I need a 90% single-sided confidence interval, alpha is equal to 10%, 2 alpha will be therefore equal to 20%, which means 100 minus 2 alpha percent means 80%. I can construct that confidence interval using our calculator. It's a two-sided confidence interval. Okay? So that two-sided confidence interval has complete alpha on the left tail, complete alpha on the right tail. Your calculator will give me this lower limit and this upper limit. Now, in this figure, I have that same lower limit, complete alpha on the lower limit. Upper limit is positive infinity, which means for upper confidence intervals, I just have to replace this upper limit with positive infinity from your calculator's output. For a lower confidence interval, do the same thing. Construct 100 minus 2 alpha percent confidence interval. Whenever you have to do 100 minus alpha percent single-sided confidence interval, we do 100 minus 2 alpha percent two-sided confidence interval. So if it is a lower confidence interval, replace this lower limit with negative infinity, keep the upper limit as it is. Done. Let's go to point number 10. Read the problem given under point 2 again and construct a 95% lower confidence interval and interpret. Also construct a 95% upper confidence interval and interpret. So, the problem given under point number 2 had 6 measurements of electrical conductivity of a certain type of iron rod at 293 Kelvin. For that question, sigma was given as 0.1. So we do Z confidence intervals because sigma is given. Let's go ahead and enter the dataset again into your calculator. Now what we need is 95% upper Z confidence interval and 95% lower Z confidence interval. That means 95% single-sided confidence intervals. Now for this question, we have alpha equals 5%. That means 2 alpha should be equal to 10%. So the first step is we do 100 minus 2 alpha percent two-sided Z confidence interval. Okay? Construct 100 minus 2 alpha percent means 90%. Okay? So this is 100 minus 2 alpha percent. Two-sided confidence intervals. So let's do that using your calculator.
Here's the dataset and the calculator, and we will first go ahead and enter this dataset into a list. To enter the dataset, I have to first press Stat, Edit, number 1, Edit, hit Enter, and we can enter all the data into the list L1. The first data point is 10.08, and then hit Enter. The second data point is 9.89, hit Enter. The third data point is 10.05, enter, 10.16, enter, 10.21, enter, 10.11, enter. Now what we have to do is I have to construct a two-sided Z confidence interval. The confidence level that I need is 90%. To construct two-sided Z confidence interval, I have to press Stat again, go to Tests, and then you have to select number 7, Z interval. We do Z interval because sigma is given. Select number 7, Z interval, hit Enter. Input method is data. Select data and hit Enter. Then enter the given sigma. Sigma equals 0.1. The list is L1. Frequency is always equal to 1. The confidence level. This time, I'm constructing a 90% two-sided Z confidence interval. Therefore, the confidence level should be 0.90. Select Calculate, hit Enter. Please make sure that you hit Enter only one time. The 90% two-sided Z confidence interval for this dataset is from 10.016 to 10.15.
So I got 9% two-sided confidence interval is from 10.016 is the lower limit and 10.15 is the upper limit. What I now need is a 95% lower confidence interval. So 95% lower confidence interval means I have to replace this lower limit with negative infinity. That's it. So this will be negative infinity up to 10.15. If I need 95% upper confidence interval, I have to just replace this upper limit with positive infinity. So this will be from 10.016. The lower limit stays as it is. The upper limit now will become positive. So this is a 95% upper confidence interval. This one is the 95% lower confidence interval. Now I will also have to interpret the meanings of these confidence intervals. So we constructed these confidence intervals for the true mean electrical conductivity. So this confidence interval says there's a 95% probability that the true mean electrical conductivity is lesser than 10.15. That's the interpretation of the 95% lower Z confidence interval for this case. Let me repeat. This is a 95% lower confidence interval. This is the upper limit. So we say there's a 95% probability for the true mean electrical conductivity to be lesser than 10.15. The same way we can interpret the 95% upper Z confidence interval. There is a 95% probability for the true mean electrical conductivity to be greater than 10.016. Okay, let me repeat. Now here is a 95% upper confidence interval. The lower limit is 10.016. So the interpretation is there is a 95% probability for the true mean electrical conductivity to be greater than 10.016. Please make sure to use those words true mean. Confidence level should be specified. Name of the random variable should be specified. In this case, electrical conductivity. And the levels, these values should be mentioned in your interpretation. Let's go to point number 11, 100 minus alpha percent single-sided T confidence intervals. And again, we do T confidence intervals when we do not know sigma. The true standard deviation is unknown. In such situations, we go for T confidence intervals. So how would you construct a single-sided T confidence interval? It is just like a single-sided Z confidence interval. I'll start with writing down the two-sided T confidence interval equation, and then from that we can derive single-sided T confidence interval equations. Okay? So we know two-sided T confidence interval for mu is given by x bar minus T half alpha degrees of freedom S over square root n. That's the lower limit. And the same way you can write down the upper limit, which is x bar plus T half alpha degrees of freedom S over square root n. Now when I need a single-sided T confidence interval, all I have to do is I can replace the critical value. Instead of T half alpha, I will have to go for the complete alpha, because in order to obtain a single-sided confidence interval, I have to keep complete alpha on one tail. For example, for lower confidence interval, for 100 minus alpha percent lower confidence interval, what I do is I keep complete alpha on the upper tail. And then I write down negative infinity for the lower limit. The upper limit will have a similar equation for this one. So I have to start with x bar plus T full alpha, common degrees of freedom, that's our new critical value, times S over square root n. And then if I need a 100 minus alpha percent upper confidence interval, T confidence interval of course, my upper limit will be positive infinity. The lower limit will have an equation similar to this one. T half alpha is replaced with T full alpha. So the lower limit will be x bar minus T alpha degrees of freedom S over square root n. Of course, these equations are not required to be remembered for the exams because we do all the calculations using our calculator. Now these equations once again tell us a way to calculate using the calculator, because the calculator will always give you a two-sided confidence interval. So, what's the first step of constructing a single-sided confidence interval using the calculator? I have to first go for 100 minus 2 alpha% confidence interval. So, in 100 minus 2 alpha% confidence interval, if I simply replace the lower limit with negative infinity, I should get 100 minus alpha% lower confidence interval. For 100 minus 2 alpha% two-sided confidence interval, if I replace the upper limit with positive infinity, I should get 100 minus alpha% upper confidence interval. Let's move on to point number 12. Rate the problem given under point number 6 again and construct a 95% lower confidence interval and interpret. Also construct a 95% upper confidence interval and interpret. So 100 minus alpha% for this question is 95%. That means alpha equals 5%. So using the calculator, what we have to do is we construct 100 minus 2 alpha% confidence interval. 2 alpha is equal to 10%, so 100 minus 2 alpha will be equal to 90%. So we will first construct a 90% two-sided T confidence interval using your calculator. Let's go to the calculator.
I must first enter the given data set. To enter the data set, I have to go to Stat, Edit, number 1, Edit, and hit Enter. To save some time, I have already entered the data set into the list L1. Now I need to construct 95% lower and upper confidence intervals. Since the calculator will only construct two-sided confidence intervals, I have to go for a 90% two-sided confidence interval. Then we can replace lower and upper limits with negative and positive infinity accordingly. For this data set, I do not have sigma. That means I must construct a T confidence interval. For that, I have to go to Stat, select Tests, and then scroll down and select T interval. Number 8, T interval. Hit Enter. Input method. Input method is data. I have already entered the data into the list L1, so input method should be selected as data and then hit Enter. The list is L1, frequency is always equal to 1, confidence level. I'm going to construct a 90% two-sided confidence interval. Therefore, the confidence level should be 0.9. Select Calculate and hit Enter. Make sure to hit Enter only one time. 90% two-sided T confidence interval is from 2015.9 to 2246.8.
So we constructed 90% two-sided T confidence interval using the calculator. So the 90% two-sided T confidence interval for mu is equal to 2015.9 was the lower limit and the upper limit was 2246.8. Now what I need is a 95% lower confidence interval. So here's the 90% two-sided interval. For the 95% lower confidence interval, all I have to do is replace this lower limit with negative infinity. The upper limit stays same, 2246.8. So how do you interpret this interval? I can say there's a 95% probability for the true mean shear strength to be lesser than 2246.8. The same way, we can also construct 95% upper confidence interval. Once again, I have to simply look at the 90% two-sided confidence interval and use the same lower limit, 2015.9, and the upper limit is now replaced with positive infinity. Now what does this mean? This means there's a 95% probability for the true mean shear strength to be greater than 2015.9. Alright, so that's it about the confidence intervals, Z and T confidence intervals. Remember one thing, when to construct Z intervals and when to construct T intervals is extremely important. If you mix those two situations, your answers will be completely incorrect. Remember again that we do Z confidence intervals if sigma is given. We do T confidence intervals if sigma is not given. That means I have to have S. Now what is sigma? What is S? Sigma is the true standard deviation, or in other words, the population standard deviation. S, on the other hand, is the sample standard deviation. We use the sample standard deviation when the true standard deviation sigma is unknown. So remember that difference between the Z confidence intervals and T confidence intervals for the rest of this semester. All right, that's it. Thanks.